So we're going to talk about energy and work and, pressure and work done by a system and all that stuff. So let's look at this question. If the internal energy of a system, is increased, the system is increased by 300 joules. This means that delta E is going to be positive 300 joules because we are increasing this. It's going to the system, right? To system. So that's positive. Oh, that looks like a negative. Let's just leave that positive. Okay, now 75 joules of expansion work is done. So that's W, and that is being work done by the system, right? So that is negative 75 joules. So that's work done by the system. So now how much heat is transferred and in which direction, to or from the system? So we know that our equation is delta E, which is the internal energy, is Q plus W. We're trying to solve for Q here, okay? So we have our delta E, which is plus 300 joules, equals Q plus W, which is negative 75 joules. And when we just add 75 to both sides, we get 375 joules equals Q. Okay, so what do we do with this number? The question asks how much heat is transferred, that's 375 joules, and in which direction, to or from the system. Okay, so if heat is being transferred to the system, then it is positive. And if heat is being transferred from the system, then it is negative. So this is the heat is being transferred to the system. Okay, and it's from the surroundings. All right, so that is the first one. Let's look at the next example. All right, so here we have a sample of an ideal gas. Okay, so we have 15.0 ATMs and 10.0 liters. These are our initial conditions. Now it expands against a constant external pressure of 2.00 ATMs. Temperature is not changing. Okay, so first of all, it says calculate the work in units of kilojoules for the gas expansion. So we need to figure out, first of all, how much it's going to expand. So we know that our work is negative P delta V, right? And we have the pressure. The pressure is 2 ATMs. So our P in this example is 2.00 ATMs. But our delta V, we're not sure because we don't know. We know that it was initially at 10 liters, but we don't know how much it expanded to. So first we have to use Boyle's law, which gives us this little hint here. Boyle's law applies. So let's kind of go down over here. And we're going to do this first. P1 V1 equals P2 V2 because we know that the temperature is not changing. The number of moles aren't changing. Okay, our P1 is 15.0 ATM and our V1 is 10.0 liters. Now our P2 is our 2.00 ATM and our V2 is what we don't know. Okay, so real quick, P1 V1 equals P2 V2. 15.0 ATMs times V1 is 10.0 liters equals our P2, which is 2.00 ATMs, and V2. Okay, so we solve for this. We get V2 equals, I forget what it is. V2 equals 75.0 liters. All right, so if we know that our V2 is 75.0 liters and our V initial was 10 liters from the problem up here, so it goes right here from 10 to 75.0 liters. So our delta V is going to be the V final minus V initial is 75 is our final minus 10 liters. That is 65 liters, okay? So now we have our work. Let's get this straight again. Work equals minus P delta V equals minus 2.00 ATM times our 65.0 liters. Okay, Sorry, this arrow doesn't really point to there. I just kind of ran out of room. All right. So 65 liters. So this means my work is minus 130 liter times ATM. Well, that doesn't really help me because it says calculate the work in units of kilojoules. So I'm not in kilojoules. I'm in liter ATM, which is really kind of weird for work. So we're going to figure out how much work we had to do. We need to use a conversion factor. So we know that 1 liter ATM is equal to 101.3 joules, right? So let's just take our minus 130 liter ATM and use our conversion factor, 101.3 joules per 1 liter ATM. And we get negative 13175 joules. Now it says in units of kilojoules. So we have to now convert that, minus 13175 joules times 1,000 joules in 1 kilojoule equals minus 132 kilojoules with sig figs and everything. There is our answer, minus 132 kilojoules. All right, next one. All right, consider a mixture. We have air and gasoline vapor in a cylinder with a piston. So that we know with a piston that the volume is going to change. The original volume is 40 centimeters cubed. Now, okay, we know that we're not going to end up with centimeters cubed for our volume, so let's just change that to liters right away. 40 centimeters cubed. We know that 1 centimeter cubed is a milliliter. So we're going to say 1,000 centimeters cubed, that's 1,000 milliliters, is 1 liter. Okay, so our original volume is going to be 0.040 liters. V initial. Okay? If the combustion of this mixture releases 950 joules of energy, so what does that mean? It releases 950 joules. That means our Q is negative 950 joules. Okay? 950 joules. It's negative because it's releasing it from the system. Okay? So it's negative 950 joules. What volume will the gas expand against a constant pressure of 650 torr? Okay, so 650 torr, we need to convert that to ATMs. We just do, 1 ATM over 760 torr. We get 0.8553 ATMs here. Okay, so we have that. Now, to what volume will the gas expand? So we're looking for delta V. Okay, we have V initial. So we know that this is V final minus V initial, and we have V initial already. We're just looking for V final. This is our question mark. It is so much easier to just solve for delta V and then stick this back in later that, we're just going to do that. So let's look at our equation. We have work equals minus P delta V. Okay, so our work, now we know that we want to use all of the heat, all of the energy of combustion is converted into work. So our work is going to be equal to this Q. Okay, so this is negative 950 joules. And we're putting the period there to show that those are all significant figures. Okay, 950 joules equals minus P. P is our 0.8553 here, 0.8553 ATMs. Okay, times delta V. Now, we're going to divide this out, and we get delta V equals 1111 joules per ATM. Well, we delta V. We need that in liters. We don't need delta V to be in joules ATM. So we're going to go back to our conversion factor where we know that 1 liter ATM is equal to 101.3 joules, right? So 111 joules, oops, I forgot a 1 there, over ATM, times 1 liter times ATM to 101.3 joules equals 10.97. Let's see, ATMs cancel, joules cancel. We're left with just liters, which is what we're trying to get to, 10.97 liters. So this is our delta V, right? This is what we solved for, delta V. So now we still have to figure this out. The V final is what we're really looking for. So if delta V, which was 10.97 liters equals V final minus V initial, and V initial was our 0.04 there, 0.040 liters. We just solve here for V final, and we get 11.01 liters. Now, with sig figs, we have to go 11.0 liters equals V final. So that is the answer to our question. To what volume will the gases expand? Okay, so here's our answer, 11.0 liters.